that discussion. So we have a kernel. It's organized as grids of blocks, meaning many blocks. Right? And each block has a certain number of threads. Okay? The entire block, meaning every thread of the block, whatever that number may be, and the limit on the recent architecture is 1024. The limit on the ones you will probably be using is 512. Okay? So up to 512 threads of a block will all be live. Sometimes, if a block doesn't use up all the resources on the SM, multiple such blocks can be live. Okay? So now your grid had 1,000 blocks and you have, let's say, 2 SMs. Each SM can fit, let's say, 16 blocks. So among the 1,000, 16 blocks will be assigned to the first SM. 16 blocks will be assigned to the second SM. Okay? And until a block is done, other blocks will wait. Now, at a given time in one of these SMs, there are 16 live blocks, meaning that everybody has a subset of the registers allocated to it, and everybody is able to read things from the memory, shared memory, global memory, wherever. And each clock, the scheduler will ask, I have these 16 blocks running. Which blocks instructions are ready? And that's a somewhat of an approximation, because actually a block need not be only 16 threads, right? And you can only execute 16 at a time. So there are some details that are not critically important. For the time being, let's just say that a block is scheduled, meaning that when a block is scheduled, whatever its number of instructions is, will run one after the other. Okay, that's not exactly the way it is, but let's, for instance, think that way, because it's not going to change anything in the general understanding. So suppose my block had 32 threads, and so I've got 16 such blocks. Every block has 32 threads, and I'll take the first block and run all its 32 threads on the SIMD, the 16 processors that I have. Okay. Once I have taken the 16 processors and run one instruction on that group of 32, I will ask which next clock, whose instruction can I run? Okay. So I've got 16 blocks to choose from. It can be the same block that I ran the instruction of. It will actually not be the same, again, for some detailed reasons. But any of the blocks which has its operands in the register is ready to execute its next instruction. Okay? And its next instruction means its 32 thread block's next instruction. So when that block is ready, you take its 32 threads, run it on one of the SMs, and next instruction asks the same question. And so as far as the scheduler is concerned, it's just a number of ready instructions to run. Okay? It doesn't care about which blocks they came from, which blocks are ready with other things. It just says, here is a group of 32, their data has arrived. That means, and there is some hardware that keeps track of their data has arrived and their operands are in the register and so on and so forth. So that flag is on, meaning its operands are there. It will execute it. Okay. Then next clock cycle, it will find something else to execute. And it's as if you are executing one big program. Okay? Because as far as the ALU is concerned, it's just every clock executing one instruction. In the CPU context, that instruction typically, all those instructions come from one thread. Here, that instruction comes from one block. Okay, one block of threads. And then the next instruction comes from another block of threads. And those two instructions may be different. Depends on whose data arrived first, who's getting data from cache, and so on and so forth.
This is the case where multiple blocks are mapped to are alive on the same SM.
Same SM.
Each block being significantly smaller than the resources each SM has to provide.
Yes.
And among those blocks, it asks which of you is ready.
Correct. And it is not unusual, right? It's quite usual that you can fit more than one block in one SM. Okay. If your blocks are big, for example, 1,000 thread blocks, then it's possible that it's only one block in one SM at a time. But then even that block has many groups of 32, right? And you can only execute 32 at a time. And so you'll say, take the first 32, execute it, second 32, execute it, third 32, execute it, and so on and so forth. Okay. And they need not be in round robin order either. Even if it is one block, it's possible that one of the 32 threads data, they can be reading from wherever they want to, comes in early and it's ready for execution, whereas another group of 32 will take several clock cycles before their data arrives. Right? So in the meantime, 3 other groups of 32, which by the way are called warps, have executed 3 instructions each, and that guy's data hasn't arrived yet. Okay, so it's only within a warp that there is SIMD lockstep, not in the entire block. However, if you want the entire block to get in lockstep, then you do sync threads. Right? That you do a barrier. You say, I want everybody to get to this instruction, the barrier instruction. And then they all start proceeding from there. Okay? So here is how you would start it. This is a very simple definition of a global function, which is how you define a kernel. So you say underscore global underscore void f. It takes an argument that's a float array. Okay, and inside it says give me my thread ID, and the thread ID is of the type which is called dim3, okay, dimension 3. So you can, if you have declared a 1D array, you will only be checking the thread IDX. Thread IDX is a pre-defined variable. Okay, you don't have to define it, and you can access thread IDX.x, .y, and .z. If you have only one dimensional array, then you will be only accessing .x.
It's the number of dimensionality.
Yes. And from the caller, for example, in this case, the main. So main is a host function, whereas f is a device function. Technically, it's a global function. It runs on the device, but its address is available on the host. Okay, because the host has to call it. So if you look at the main function, it says f, those open close brackets, some information about how many instances of this to be run in the kernel, and the parameter is a. Okay, a is the parameter that's going to be available to all the threads which are going to participate in this kernel. Okay, 1n here says that we are executing one block. One is the dimension of the grid, and the block size is n threads. Okay, n is defined somewhere.
That means one grid having n blocks.
One grid having, you always have one grid, right? How many blocks in the grid is the first thing. In this case, there is only one block. There is only one grid, right? The kernel can be thought of as the grid. This kernel is associated with one grid, and how many blocks you want to run are independent units, somewhat independent units, and then the size of the block, which is more tightly coupled set of threads. And so here n threads in the block, one block in the grid. Okay. Now all the object-oriented parts of C++ are well supported, but on earlier versions there was some bugs and issues with virtual functions and instancing and all that kind of stuff. So you may want to just stay with basic C style programming. You can make classes, but don't get too innovative. Okay, so the configuration is how you say how many times, how many blocks in the grid and how many threads in each block.
So I have a doubt in the previous slide. So you said this is available as a data array, right? The whole code within the kernel is available in the global memory, accessible to CPU, so that it can call
Global memory?
Global as in accessible to both. Global.
No. So global is not even visible after it has been compiled. Okay, that's something that's processed by the high levels NVCC compiler. Okay, so when I am saying that it's accessible, when I said it's a data, everything that function f compiles to is the set of instructions is basically data as far as CPU is concerned.
Okay. That is available visible to CPU.
Yes, but not from your program, right?
Not from my program.
Yes.
So, but you said that it needs to call it, right? The CPU needs to call this function in some sense. Then what does it do after calling? Because it doesn't have to do any work after calling it, right?
There are. We will come to that. There are synchronous and asynchronous calls, just like MPI, if you recall. And for synchronous calls, you have to wait for that function to return. Okay. It turns out that when you invoke a kernel function, that's a synchronous call. And so you have to wait for that kernel to return. There is a way to stream these kernels, and you can turn it into asynchronous calls. We hopefully will talk about that. That's not necessary to understand the basics of CUDA. You can even read that up later. Okay, so among the most important changes to C is this configuration, right? 3 less than, 3 greater than, and you've got 2 variables, constants, whatever, separated by a comma. These each can be an integer, just like it was in the previous example. But when it's an integer, that means it's a 1D array. If you want a higher dimensional grid or block configuration, then you have to use one of those variables, predefined dim2 or dim3 for 2D and 3D arrays. Okay. What you cannot do is have different blocks of a grid be different size in terms of number of threads, right? Because this is basically A cross B type definition. What you cannot do is in the middle of the kernel say now create so many more threads. So those are some of the limitations. As I had mentioned, all threads which are within a block are scheduled in groups of 32 called a warp on the same SIMD. They will have access to the same shared memory, but 2 blocks, because you don't know whether they are going to be scheduled on the same SM or on different SMs, cannot share each other's shared memory, cannot see each other's shared memory. And that is filtered or that becomes visible in the programming model also, because you cannot allocate shared memory for multiple blocks. So from a thread's point of view, what is something that is totally owned by the thread? Registers, because no other thread, even within your block, can see what's in your register or even knows about your register, cannot address your register. There is also non-register space called thread local memory. It's like local variables of a thread, which resides in the global memory. Okay, so that once you understand it, it's not confusing, but the names are somewhat unfortunate. It's called thread local memory and it lives in global memory. But it's thread local in the sense that scope is local. Only that thread knows what's in there and no other thread can address it. Okay. Then there is shared memory beyond the thread, and you can see what other threads are writing of a block are writing into the shared memory, and when you write something into shared memory, other threads can see it. And then beyond that is global memory, which means when you write something to the global memory, any thread of any block can see it eventually. Right? There is no guarantee of any consistency, except that when you write something and somebody else writes something, either your data or that somebody else's data gets written. Right? It's never that half of your data and half of somebody else's data gets written. So if you write 69 and somebody writes 37, it'll never be that the data in the memory is going to be 1. Okay, it's either 69 or 37, but there's no way of knowing unless you do some synchronization, which is going to get written. Okay. There's no guarantee that different threads of different blocks will see anything in the same order. Okay, so you have to ensure that must happen. There are guarantees within a block. There are very clear guarantees within a warp, because they are all executing in lockstep fashion. But overall, there are no guarantees. Okay, so this is some more of that discussion that we were just having. And this thing says there are only 8 SIMD processors. That's the previous generation. The current generation has 16 of them. But in both generations, the notion of a warp is 32 wide. Okay, so there are 32 threads that are going to execute in SIMD fashion. Right? Meaning that if some instruction of one of these 32 executes, you can be sure that other 31 have executed that instruction. All right. This is not guaranteed across warps of even one block. And there is also this notion of half warp, which comes from the fact that there are 16 actual processors. Right? So half warp is actually physically being executed together. And the full warp is executing one after another, precisely one after another. Right? So why can we guarantee that if your warps instruction 5, I have seen a given thread has seen instruction 5 and is going to instruction 6, then every other thread of that warp has finished execution of instruction 5. Why? In spite of the fact that only half warps execute in real SIMD fashion.
Executed one after another strictly, that's right.
Strictly, right? So once you have executed 5, your 6 cannot begin until the other half has also executed 5. Then your 6 begins, then that guy's 6 begins. Okay, so It's still in lockstep fashion. There is a notion of branching within a warp, as I had earlier mentioned also. Meaning you can say if my ID is even, then do something. If my ID is odd, do something else. Right? So half of them will be doing one thing, the other half doing the other. There is significant overhead to this branching. One is clearly that when one is live, so suppose you say if my ID is odd, do something. Then the SPs on which the thread ID is turning out to be even, those clocks will be doing nothing. So those clock cycles are being wasted on those processors. But there is also significant overhead in collecting the data together. So when you have this divergence of execution, then at some point they're all going to probably converge. Right? So you can diverge, and the execution unit has to keep track of which are the live ones that are going to execute now and which are the ones that are going to execute the else part if there is one. Right? So that keeping track of this divergence and then eventual convergence has significant overhead. And as a result, the newer architectures have this notion of each instruction, or rather each thread of each warp, being separately enabled or disabled, right? Which is not exactly the same thing as convergence and divergence. Right? They all are basically not diverging at all. Every instruction is being executed for all of them, but some of them just happen to do nothing. Okay, nobody is keeping track of if part has been executed, now let's execute the else part on the ones that were inactive in the previous phase. So in divergence, the hardware is keeping track of, I've executed the if part, thread numbers 1, 7 and 9 had the condition true, others had false, right? So it has to keep track of, now I have to go to the false and execute them, right? So that's the way instructions get scheduled. But in this case, you keep every instruction as a complete full instruction. There is no if else. Right? It's simply a mask that says which of the SPs are going to execute this instruction. Right? So now the compiler, this is typically done for simple loops where you say if X do something, else do something, right? So it will generate two pieces of code, and in one piece of code it's going to keep everything that is going to execute to true, enabled. The other piece of code, it's going to keep everything disabled. Okay, so the hardware is relieved the extra overhead of keeping track of this.
The condition check would happen at runtime.
Condition check can happen at runtime, right? So that once you have that condition check, that mask can be set, right? And then there is instruction to negate the mask, and then you do the other thing.
But this switching needs to be done for each processor individually.
Yeah, so switching is just negate the mask. So that's also an instruction that says negate the mask. So these instructions didn't execute earlier or didn't exist earlier. Now they do. 16 processors executing 32 things. We've talked about this dimension business. The only thing that you need to be aware of, or it's important to note, is that effectively it turns out to be column matching, because it comes from the XY, where X is on the horizontal axis, Y is on the vertical axis, and you access something by XY coordinate. So X becomes column and Y becomes row. X becomes column, right? How far? So X is equal to 0, 1, 2, 3, 4, 5, 6, and Y is 0, 1, 2, 3, 4, 5, 6. And so for example, when you have a dimension that is, what does it say? A cross B, then, and it has A cross B cross C. So it's A cross B cross C, then the indexing will work out to be B dot X. So usually it would be K would be the fastest varying variable, right? I times one 2D array, J times the row number, and then plus K. Here it's the opposite. It's B dot X plus Y times the X dimension, and Z times X dimension times Y dimension, right? So it's just the opposite of row measure. And so that's what's demonstrated pictorial. Okay, X is horizontal axis. X is the horizontal axis written in the wrong place. It is actually moved to the wrong place. It was written in the right place. X is the what's been drawn here as horizontal. Okay, Y is what's being drawn here as vertical, and Z is one going into. All right. Other than global and shared memory, there is constant and texture memory. Okay. Both of them are cached. It turned out that in the previous architecture, shared memory and global memory were not cached, meaning that every time you read some data, it actually needed to come from the actual memory, DRAM. Now everything is cached. The only difference is that the constant and texture memory is read-only, and its paths are read paths are optimized, and you cannot write to it. It is possible, because constant and texture memory are both actually physically in the global memory. It is possible to alias that address. Right? So somebody else sees the same address as global memory and can write to it. If you do that, there is no guarantees over what will be read by the read-only part, or by somebody else who's reading. Okay.
So in the memory, the global memory is a cache.
Global memory is not.
Is a shared memory.
Say that again.
The global memory is a cache. Then you have a scratch pad for individual SP.
No. Global memory is not a cache. Global memory is the memory which sits off the chip, right? It's got its own DRAM chips, and there is some bus that leads from the main CPU to this global memory. Shared memory is kind of like cache. It is on-chip cache, except it doesn't behave like cache in that it doesn't have cache lines defined, it doesn't have tags defined to figure out what's in cache, what's not in cache. It doesn't have an automatic fill and snooping and discard policies.
So the cache in the GPU is like shared memory. Then what is scratch pad?
Scratchpad is the shared memory.
The cache.
There is cache separate outside of the scratchpad. I'm going to, since we are anyway at the end of the time,